This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Survey of Immersive Analytics. Adrien, Fonnet, and Yannick Pre-E. Abstract: Immersive Analytics, IA, is a new term referring to the use of immersive technologies for data analysis. Yet such applications are not new, and numerous contributions have been made in the last 3 decades. However, no survey reviewing all these contributions in 29033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Index terms: Immersive Analytics, Survey, Virtual Environments, Immersive Environments, Data Visualization, Information Visualization, Scientific Visualization, Visual Data Mining. Introduction. Immersive Analytics, IA, was defined in 2015 as the applicability and development of emerging user interface technologies for creating more engaging and immersive experiences and seamless workflows for data analysis applications, 1, and more recently as the use of engaging, embodied analysis tools to support data understanding and decision-making, 2. The idea to use immersive technologies to carry out visual data analysis tasks is not new, 3, and many proposals have been made since the early 90s. Indeed, the interest of researchers in the use of immersive technologies has been driven by the ability to represent 3D data in 3D, as well as the possibility to better exploit human perception capabilities, and to make use of embodied perception and interaction. The contemporary development and structuring of the field, attested by scholar meetings 4, 5, and conference workshops 6, 7, 8, 9 in the last years, is mainly related to recent technological breakthroughs providing affordable and high-quality immersive hardware and software. 1.1 Method: Corpus Building and Analysis. 1. Since no clear IA domain had been established before 2015, no particular venues or keywords specifically gather contributions together. We therefore conducted a systematic but open investigation with the main scientific search engines, IEEE Explorer, ACM Digital Library, Science Direct, Springer Link, or Google Scholar. Using search terms that cover both data analyzed processes, e.g. visual data mining or data visualization, and immersive technologies, e.g. immersive environment or virtual reality. Specific journals, conferences, and workshops were also covered, such as TVCG, IEEE VIS, or IEEE VR, as well as the full bibliography of key scientists. The search stopped when papers' references were not bringing any new articles to the survey's collection. This availability of supporting technology led to a rising number of system proposals and scientific contributions. However, no survey article has been published that would help newcomers embrace the variety of 3 decades of developments in IA. The most notable surveys in the field focus on specific scientific domains and do not cover IA as a whole. For instance, Bryson et al. 10, Simpson et al. 11, and Van Dam et al. 12 focus on scientific visualization through the use of virtual reality, VR, technology, and Ben Said et al. 13 focus on visual data mining exclusively. Therefore, our aim is to provide readers with an exhaustive survey of IA works from 1991-14 up to the present day. In particular, we want to provide a quick access to all the technologies, sensory mappings 1, and interaction techniques that have been implemented in IA systems, as well as proposed directions worth investigating. A. Fonnet and Y. Pre are from LS2N UMAR 6004 CNRS University of Nantes. Email: Adrien.Fonnet, Yannick Pre@universal-nantes.fr. Manuscript received December 20th, 2017, revised February XX, 2018. 1. We use the term sensory mapping over visual mapping since IA systems are meant to use all senses. The initial criterion for a paper to be included in our corpus was that it must contain a thorough description of an immersive analytics system. First, we favored the definition of 1 over that of 2, since it provides clearer limits and therefore is better suited for a survey paper. Second, as the visual channel is the most commonly used to provide immersion, we considered that the emerging user interface technologies of 1 must at least have 3D graphics, stereo, and head tracking, see Section 2. Third, the systems had to be interactive, i.e. at least with navigation and selection, for users to perform data analysis, i.e. explore data representations and gather insights. However, our criteria excluded many papers that we deemed important, especially after so many years without a survey covering the domain, such as evaluation papers focusing on the effect of rendering technology, or position papers discussing the future of IA. That is why we also included papers without full IA system descriptions, but that clearly stated in there. Introduction that their goal was to contribute to the design of interactive immersive systems supporting data analysis. The search, completed by the end of year 2018, constituted our corpus, N equals 177. The analysis of the publication dates, Figure 1, shows a steady increase, with a slight peak in the late 90s and a recent burst. Initially, the corpus revealed the domination of 2 main types of papers, those describing an IA system and those. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. Figure 1. Literature corpus over the years. Related to evaluation linked to IA research, papers could be both. For each type of paper, we further extracted relevant information in a systematic way. For the system papers N equals 127, 2, we extracted the system name, target users, application domain, and the purpose of the application. We categorized systems by immersion category, leading to 104 papers concerned with virtual reality, VR, 15 papers with augmented reality, AR, and 6 with wall displays. 2 papers, 15, 16, used an atypical solution. That is why their category remained blank. We also described the rendering technology used to display the visualization. Then we focused on the data, gathering the description of the dataset used by the application and its main category. Dataset categorization was inspired by Schneiderman's taxonomy, 17, and resulted in the following distribution: spatial, 36 papers, temporal, 7, spatiotemporal, 43, multidimensional, 24, and graphs and trees, 17. We also described sensory mappings, i.e. how the dataset attributes were represented in the visualizations. Moreover, we systematically analyzed each system according to the low-level interaction tasks it allowed. These tasks, based on the taxonomy of Bremer and Munzner, 18, are the following: navigate, select, details on demand, arrange, change, filter, aggregate, annotate, import, derive, and record. If a task was available, we completed its description with the input devices, the action to be performed, and the output. Last, we checked if the system featured collaboration. There were 15 papers that adhered to this criterion, and we completed their description by capturing aspects of the collaboration, such as synchronous/asynchronous, same/different physical place, same/different visualization, and modes of communication. For the evaluation papers, N equals 68, we split the category B. Tween IA system evaluations, 28. Evaluations comparing IA with non-IA systems, 26, and evaluations assessing which technologies, representations, or interactions were better within the same IA system, 14. We extracted data types and representations, dependent and independent variables, tasks, quantitative and qualitative results. The remaining papers, N equals 21, were categorized based on their type, i.e. survey paper, position paper, or framework, and the main idea they conveyed was described. 1.2 Structure of the survey. The main objective of the survey is to provide a quick access to all the technologies, sensory mapping, and techniques. 2. Those systems are described in more details on the companion website app //www.immersiveanalyticsurvey.org. 2. That have been implemented in IA systems over the last 3 decades. Based on the quantity of papers describing IA systems and the quantity of information to convey, we decided to focus our survey on these papers. That is why the first 4 sections are dedicated to the description of IA systems. To ease the reader's understanding, we start in Section 2 by presenting the various immersive technologies used, so as to provide a description of the physical systems. Then, we focus on data representation and analysis goals in Section 3, summarized in Table 1, and on interactions means in Section 4, summarized in Table 2. Section 5 is dedicated to the study of the specific aspects of collaborative IA systems. Section 6 then covers evaluation papers. Our second objective is to determine the main challenges of IA and directions worth investigating in the near future. Each section ends in a discussion, while Section 7 gathers RF endings and builds upon them to outline some orientations. For IA. Technologies. Various technologies have been used in IA systems. Our choice to determine if a technology is immersive is to focus on its fidelity aspect, instead of considering a presence feeling, as stated by Slater, 19. Therefore, our criteria in this paper are that those systems must offer 3D graphics, stereo vision, and head tracking. In each subsection, we focus on one immersive rendering technology and on the main associated input devices, following a chronological order. See Figure 2 for an overview timeline. 2.1 Boom. Binocular Omni Orientation Monitor. The Binocular Omni Orientation Monitor, BOOM, is a counterbalance CRT-based stereoscopic display implemented in 1990-20. It is composed of a robotic arm fixed on the ground with each joint angle managed by microprocessors and motors to ensure moving the structure requires low energy from the user. A stereoscopic display is located at the end of the arm where the user places his head to enter the immersive environment. Position and orientation are computed owing to sensors located at each joint. This system was used by Bryson et al. To implement scientific visualization applications, such as the virtual wind tunnel, 14. The goal of the system was to effectively visualize 3-dimensional unsteady flow patterns to understand them despite their complexity. It allowed the user to inject particles and observe their trajectories within a pre-computed unsteady flow, 3D vector field, while the simulation was running. Distributed computing was employed to ensure interactivity and attain the minimum frame rate, 8 frames per second, required to guarantee immersive illusion, 21. One cluster of computers was dedicated to compute the result of the simulation and a second to compute the visualization's rendering, both communicating through a network. All BOOM IA systems used 2 input devices, a classical keyboard and a data glove. The ease of entering and leaving the immersive environment made it easy to use a keyboard to change visualization parameters, although it broke immersion. Data glove interaction in immersion used electromagnetic field tracking, which required the control of. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Figure 2. Timeline of the rendering technologies used to implement immersive analytics system. The workspace environment not to disturb the measure, as well as a calibration phase prior to each use. 2.2 Surround Screen Display. The first surround screen display technology, called CAVE Automatic Virtual Environment, CAVE, was implemented by Krusnera et al. In 1993-22. This initial implementation consisted of 4 walls, right, front, left, and floor, each one associated to a 120 Hz projector. Head tracking was managed via electromagnetic sensors, allowing the capture of the position of the stereoscopic glasses. The CAVE was used for scientific visualization, e.g. simulation about the formation of the universe, 3D reconstruction of MRI data, or climate data visualization. 23. Multiple concessions had to be made to reach the required frame rate, 10 frames per second, e.g. limiting the size of the dataset, simplifying algorithmic calculation with approximation, and decreasing the quality details of the rendered scene. 24. Multiple declinations of the CAVE were implemented during the first decade of the 21st century, with different numbers of walls, from 2 to 6, of varying sizes and hardware improvements, cluster of computers, projectors, tracking technology. 3. Systems. Another characteristic of Fishtank VR was the use of a keyboard as the main source of input, since the overall setup is close to a 2D desktop. Where et al. Used this technology to visualize object-oriented software with a network representation. They confirmed their initial hypothesis that adding an immersive component to a system, i.e. stereo and head tracking, increased both the perceived and understood information for graph analysis. 32. 2.4 Responsive Workbench. The Responsive Workbench appeared in 1995-33. It used stereoscopic glasses and external head tracking with a projection-based horizontal screen. This choice was made to target specific workers for whom the workbench metaphor, i.e. working over a table, was deemed useful, such as doctors, medical training, automotive engineers, wind tunnel, and architects. Architectural design. 33. Input devices were diverse. Data glove. 34. Wand. 35. Or tracked stylus. 36. The next decade led to more radical changes. Allosphere is a 10-meter spherical-shaped cave built in 2007-25. The associated Allobrain project led to the implementation of an IA application for immersive navigation of brain data extracted from functional magnetic resonance imaging, fMRI. 26. The Cave 2, 27, and the Reality Deck, 28, are cave-like systems that were built respectively in 2013 and 2015 from the ground up for IA, focusing on the collaborative aspects of data analysis. These systems use tile display instead of projectors, greatly improving the resolution over classical cave. Floor projection was also discarded to ease the occupation of the central space by a full team, hence cutting on the immersion to provide more physical collaborative space. The main sourcio finput for CA viewer 3 dmeistract over 6 degrees of freedom with multiple buttons and a joystick, called a wand. They combined the advantages of introducing the position of the user's hand to the virtual world with a simple controller input. A few works also explored the use of data gloves in Cave 29, 30. 2.3 Fishtank VR. The Fishtank VR concept was introduced by Ware et al. In 1993-31. It consisted of a monitor screen combined with stereoscopic glasses and an external head tracker, providing all the required components for an immersive experience at an affordable cost. The field of view was limited, but resolution and brightness were superior to projections-based. Like the Cave and the Fishtank VR, such systems only provided one user with the correct perspective, which led to issues in collaborative settings, e.g. finger pointing to show a point of interest, did not work. A two-user solution for the responsive workbench was developed in 1997. Both users had head tracking while the screen displayed 4 images per frame. 2 users, 2 images for the stereo. 37. 2.5 HMD, head-mounted display. Head-mounted display, HMD, has been used to render immersive environments since Ivan Sutherland's first prototype, 38. However, the small resolution of the system was judged unfit for data analysis until the late 90s. Indeed, the oldest IA references in our corpus that use HMD were published in 1997 with the Virtual Data Visualizer for VR Molecular Data Simulation Analysis, 39, and the Studierstube. For augmented reality, AR, dynamical system analysis, using the Virtual I/O eyeglasses, 40. Use of HMD remained sparse in the context of IA after year 2000, with only a few attempts, e.g. 41, 42, but the arrival of the Oculus Rift DK1 in 2012 brought about a renewed interest. This first version was still limited due to the lack of positional head tracking, and researchers had to overcome this first hurdle with external tracking systems to generate proper immersive environments, 43. The last generation of HMD, such as Oculus Rift, 44, HTC Vive, 45, Meta One. 46, or Microsoft HoloLens 47, provided high resolution, stereoscopic rendering, and head tracking while remaining affordable, putting them in a perfect position to become privileged IA hardware for the years to come, 48. HMD systems have been associated with various input means for IA. Data gloves were used in the late 90s. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. E.g. in 41. The use of bare hands movement was later explored to interact with the virtual or the augmented world, with Oculus Rift HMD and Leap Motion, 49, Trackers 50, or HoloLens 51. IA researchers also rapidly adopted controllers as soon as they were shipped with VR HMDs, e.g. HTC Wand and Oculus Touch, 52. IA HMD-based systems have mostly been designed for standing users. HMDs have also been used for IA in conjunction with high-resolution displays. For instance, Nagao et al., 53, used the Meta One with a 8K screen, allowing the preview and tuning of parameters of a visualization in the HMD before computing the entire scene for the screen, thus saving a lot of computation power and ensuring adequate frame rate while managing complex visualizations and datasets. Another approach was to provide dedicated information in the HMD while a main screen notable with said for shared information in collaborative settings, 54, 55. 2.6 Discussion. The rendering technologies used in IA are constantly changing. The BAOM wassasid in the Nindias, but there is no mention of it in our corpus after 1994. The cave had to evolve to remain relevant, switching from projectors to tile display. Fish tank and workbench systems have been widely used, but not so much in the past few years, maybe because of the current focus on HMDs pushed by the gaming industry. In addition, a variety of new input devices have regularly been proposed that open the design space of interaction possibilities for IA, such as data gloves or trackers which allow the tracking of all 6 degrees of freedom of any object they are attached to. It must also be underlined that in the past 6 years, the most used immersive technologies, HMDs, have not been built with IA as their main target, and researchers using them had to compose within their limitations. As a conclusion, the lasting IA dependency on the relatively volatile available technology may have induced volatility in the field, which is still struggling to develop its core concepts and techniques. Data and sensory mapping. Various categories of data have been used for immersive analytics. We considered the 5 categories defined in Ben Schneiderman's taxonomy: 17, spatial, temporal, spatiotemporal, multidimensional, and graphs and trees, and we focused on data representations and sensory mapping. We use the term sensory mapping to describe the projection of data attributes onto sensory channels as a generalization of visual mapping that is more appropriate for IA. Table 1 provides an overview of the papers presented in this section. The column category is based on Nesbitt's 4 main modalities to encode data: 56 spatial, visual, sound, and haptics. The spatial category has been renamed as position to avoid confusion with the spatial data type. 3.1 Spatial data. Being spatial in nature, immersive environments are a natural choice for presenting spatial data. Position is the main channel used to encode spatial data information, with 2 main approaches. Data elements can 4. Be placed on top of a map or relative to a 3D model. For geolocalized data, the Battlefield Decision-Making Dragon System, 35, displayed units over a 3D representation of a map at the location of latest report. A similar application was recently proposed to help fight against maritime smugglers and coordinate action between agencies. 55. Entities such as boats and drones were displayed on top of a tangible map of the maritime shore using AR. Archaeological systems also use such mapping by placing each found item at its position of extraction over a representation of the excavation site. The Archive system opted for a flat dark gray texture to represent the excavation site, 66, 67, while VITA, Visual Interaction Tool for Archaeology, 42, and ArtifactVis 2, 68, implemented photogrammetry. The Endurance Project, 57, proposed a reconstruction of Lake Boney in the Antarctic on top of which measurements, bathymetry scanning, and water chemistry profiling were positioned. Lechner et al. System 127 allowed visualization of water chemistry measurements made in the mid-Atlantic states of the USA. Viarge E59 displayed a 3D representation of Earth mineral resources showing various layers and measurement uncertainties. Mahmoud et al. System 58 supported biodiversity analysis by displaying animal species locations over multiple 2D maps occupying the 3D volume. Other proposals used virtual or real 3D models as their base for spatial data placement, mostly in the medical imaging context. Some systems proposed 3D model of brains reconstructed from CT, computerized tomography, MRI, magnetic resonance imaging, and fMRI, functional MRI, data 60, 62, 64, 128. This type of 3D body model representation could also be complemented with 2D slices for doctors to import their previous scans inside the immersive visualization, 63, 69. Instead of using a classical network approach with force placement algorithm, Kirais et al., 65, took advantage of the spatial structure of the brain to place connectome data in their neurocave system. Each node was located at its true position in the brain. Gillett et al., 61, placed electrostatic field representations using AR around a tangible model of a macromolecule. The AR ARSIM tool for industrial factory layout planning allowed users to modify layouts in situ and then visualize the production line. 51. Visual. The main strategy for representing geolocalized data elements is to use 3D glyphs. Several archaeological systems described findings by associating shapes to findings types and colors to cultural origins or materials. 42, 66. The Dragon System, 35, represented troop squads with boxes and more prominent units, tanks, ships, and planes, with 3D models. Color, opacity, and 3D icons were used to depict allegiance. Allied units were represented with a semi-transparent blue texture with an American flag located next to them, while enemy troops appeared with darker red skull flag. Color was also used in medical imaging to encode transfer function, 64, or degree of anisotropy, 128. Sound was used by two systems in our corpus. Fr. Aulick et al. 70 proposed a system to analyze well-logged data where one numerical attribute was encoded using a Geiger counter metaphor, the velocity of the ticks indicating the value of the attribute. Lombardo et al. 71 proposed a visualization of macromolecules using solvent extruded surfaces for ligand-receptor interaction study. The selected ligand emitted a 3D 1077 to 2626, c. 2019 IEEE. Personal use is permitted, but republication/redistribution requires IEEE permission. SEEP www.ieee.publications_standards/publications/rights/indexed him for more information. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IEEE Transactions on Visualization and Computer Graphics JOURNAL-OFTVCG, VUELD, XX, NO-DID X, month 2019 5 Table 1. Overview of T sensory mappings proposed in the literature data type category sensory mapping references geolocalized data on top of a map representation. 35, 55, 57, 58, 59, position localization over a 3D model, 60, 61, 62, 63, 64, 65, 3D model, 35, 51, 55, 61, 64, 3D glyph, shape, color, opacity, 42, 58, 59, 65, 66, 67, 68, visual texture. Tooth slice in medical imaging, 63, 64, 69, Geiger counter metaphor. 70, sound simpleton atoidicate structure presents. 71, spatial. Haptic surface force feedback, 72, 73. Position 3D scatterplot, 74, 75, 76, 77, dots, 74, 78. Visual basic shape with color, 75, 76, 77 sound. Temporal haptics, particle/molecule position and simulation volume, 14, 39, 79, 80, 81, 82, 83, 84, 85, geolocalize data on top of a map representation, 37, 50, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, position X store present non-spatial attributes, 39, 90, 91, 99, 100. Size of 3D object, 95, 101. A rows 4 vector field, 82, 88, 89, 101. Isosurface, 82, 88, 89, 101. He map, 94. Colors, 37, 39, 79, 84, 90, 91, 92, 94, 97, 101. Visual line of store present trajectories 37, 93, 94, 97, 98, 99, mid-no test store present an average value 80. Sound air rushing metaphor 81, spatio-temporal haptics, 3D scatter plot 41, 102, 103, 104, 105, 106, 107, 108, 109, parallel coordinates 52, 110, based on clusterization algorithm 111, 112, position based on querisult 113, colors 41, 102, 103, 104, 105, 106, 108, 109, 113. Size 41, 102, 103, 104, 105, 106, 108, 109. Shape 102, 103, 104, 105, 106, 108, 109, 113 texture. 106, 109 DOP dynamic object properties. 104, 108 visual line. 52, 110, 113. Spoken number 4 categorical attribute. 108. Sound pitch interpolation for numerical attribute. 108. Multidimensional haptics. Node/edge diagram. 32, 114, 115, 116, 117, position encapsulation of filament. 118, 119, 120, 121, 122, 123, 124, 125, 126, city metaphor, 118, 121, 124, 125, 126, other metaphor, world, solar system, 119, 120, 121, 122, 123, visual nodes/edge properties. 115, sound. Graph Santry's haptics. Sound to indicate its localization. Sought hat its position was always available to HuServe and when Euclided. Haptics was and lyozid systems, both dedicated to macromolecular visualization. Those are beingable tofiel, the outside surfacey spheres. 72, 73, or the inside-off curved tubes. 73, with a haptic pendivis. 3.2 temporal data temporality seems to be underrepresented in URCIS. We hypothesize that this is due to its non-spatial nature and its arguably complex nature compared with multi-dimensional or graph Santry making jittles attractive for immersive environments. Position. Moore et al. 78. Proposita system to investigate the financial data of the university cave, considering budgets, departments, and number of students over time. They introduced the concept of in particles where each data point was represented by a particle generated by a circular C point that represented a specific table of that tacit. Each particle had a limited time span based on the actual time span of the entity in the university, and ways affected by attractive forces generated from filters. See section 4.6 former details. Nespatetal, 74. Implemented a NAI system to support traders in their stock market data analysis. Time MUIS represented with an axis and the time Windorjed fro single datos severalments, stock prices, volumes. And move and gaver a price so vera period were rinko deducing tormaining gaxist. Hellovis. 77. Wasseradar signal Ayatul Thadalode signal. Intelligence operators to determine a tesorcio fetch signal. Data points. Were placed in alicals kale presenting timed. The idea. System. 75. Present edisers activity log sesa 3 cylindrical scatter plot. Each axis encoded off theme and attributes. Date, time, users, and event types, and was represented beyond with ticks and labels. Debug AR. 76. Presented distributed system logsto programmers for debugging purposes. Each event was represented by a sphere in nogmentadrilation topofadable placed horizontally on a desk. Haten cadeted time. Decorentinalized time step being placed dathadescolval. The message exchanged between systems were encoded via line. Visual, color is largely used to provide additional information about temporal detailments. Hellovis. 77. Used color to encode frequency, level, or width off the pulse, idea. 75. To encode event types. In debug AR. 76. Data points and lines colors respectively encoded the system emitting the logs and the deeps of messages. Sound and haptics were no exploited for temporal data. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information, DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. In the papers of our corpus. 3.3 Spatiotemporal data. Spatiotemporal data have been used in IA systems since the virtual wind tunnel. 14. See section 2.1. Displaying results of 3D simulations with both complex and inherently 3D data was indeed one of the driving forces that pushed the development of IA systems. Position is logically used to display spatial positions of simulation data. Molecular simulations have been visualized in immersive environments to provide insights to chemists and doctors, e.g. deep understanding of drug-compound interactions, 39, 79, 80, or blood damage analysis, 85, showing particles at their computed location for each time step. CFD simulation used 3D flow fields 14, 81, 82, 84. Moreover, as it was the case for purely spatial data, temporal geolocalized data have also been largely used in IA systems. One important domain is atmospheric and oceanographic data analysis to support climatologists, objects of interest being placed on top of map representations 50, 86, 87, 88, 89, 90, 91, 92, 95, 101. Trajectory data are also geolocalized data, but are represented by lines that cover the full duration of the trajectory instead of discrete elements. 37, 93, 94, 97, 98. Cunningham et al. Allowed users to explore law enforcement's texts. Logs 96. They represented each text entry with a graph of its named entities, figured as icons and relations, the icons being linked to a 2D map if they referred to a location. Interestingly, a few works used one spatial dimension of the environment to represent non-spatial information. The virtual space-time allowed physicists to observe the complex geometry of curved space-time by displaying geodesics 99, with one dimension encoding the time. The virtual data visualizer 39 could encode molecule velocities on one spatial dimension, similarly to 90, 91, which displayed the power of earthquake on the height axis. The tangible Braille plot 100 was a supportive system to analyze movements of entities, e.g. people or vehicles, around a location of interest, LOI. It used a cylindrical coordinate system where radius and angle encoded the distance and orientation from the LOI and height the time. Visual. Flow field for CFD simulation have been represented with arrows providing direct perception of the direction and orientation of the flow, 1482. Similar representations have been used for atmospheric simulation and analysis to represent water and wind flows, 86, 87, 101. Isosurfaces could represent environmental variables, e.g. temperature, water density, or pressure, 86, 87, 88, 89, 101. Color has been used for all types of spatiotemporal data. The Virtual Data Visualizer, 39, used it to encode molecule velocity, 84, for air pressure, 90, 91, for the magnitude of the earthquake, 92, for the diseases category of a new reported case, and iFlight, 94, for the bee's roles or behaviors when analyzing bees' trajectories. Color gradient was used in 97 to display the orientation of plane trajectories, line width encoding traffic. Last, 95 represented weather precipitation values as measured by sensors directly with the heights of a 3D bars. Sound has been used in 2 papers. Wesk et al., 81, used sonification to display the flow field magnitude of A. 6. CFD simulation with an air-rushing sound metaphor, 80, used it to display the overall energy of the molecular system in the current simulation step by playing a specific pitch. Haptics has not been used in any paper of our corpus to encode attributes of spatiotemporal data. 3.4 Multidimensional data. Systems in this section have all been designed for visual data mining, where users try to obtain insights from correlations, clusters, or outliers. The datasets vary a lot, from classical machine learning iris or wine databases, 106, 112, to CAR 107, 129, demographic 41, 52, 102, genomics 111, 130, or forest databases, 104, 105, 108. Position is most commonly used to encode one attribute per dimension of the 3D environment, effectively creating 3D scatterplots. Indeed, 11 papers out of 17 use such representation, 41, 102, 103, 104, 105, 106, 107, 108, 109, 129, 131. Other possibilities have been explored, such as 3D parallel plane coordinates, 52, 110, projected 2D scatterplots corresponding to the physical position of the user within the virtual environment. 130, algorithmic positioning with SOM, self-organizing map, 112, or BLAST, 111, user query based so that relevant data points move close to the user, 113, or even self-created by the user with IMAXs, 129. Visual. Additional attributes of 3D scatterplots data points have been encoded using various visual channels. Color, 103, 104, 105, 106, 108, 109. 131, shape 105, 106, 108, 109, size 103, 105, 106, 108, 109. 131 or texture, 106, 109. The 3D 3D visual data mining approach added dynamic object properties, proposing to use vibration, rotation, or blinking of 3D glyphs to encode additional attributes, 104, 105. For parallel plane coordinates, the line's colors were used to encode more information and declutter the visualization, 52, 110, 129. The sound channel has only been used once in our corpus to encode numerical and categorical attributes in a second version of 3D-DM, 108. The numerical attributes were represented with pitch interpolation and categorical attributes with spoken numbers. Only the data points in a sphere centered on the analyst were emitting sound, the analyst controlling its diameter. The haptics channel was not used by the papers in our corpus to encode additional attributes. 3.5 graphs and trees position. Software visualization has been one of the driving domains for tree data use in IA, with the objective to make it easier and faster for code maintainers to familiarize with source code and detect important and interesting areas in it. Most systems used a city metaphor to represent source code: 118, 119, 120, 122, 123, 124, 125, 126, position being used to organize elements based on their proximity in the tree. For graph data, node placement has generally been determined by force generation algorithms to limit the occlusion of the node link visualization: 32, 114, 116, 117. Visual. FileVis 1998, 118 represented each file with a pedestal with an icon depicting its type, sphere for definition or cylinder for declaration. Color similarity. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. Indicated two pedestals had the same file names. Small blocks representing functions were placed on pedestals, the block's heights encoding the number of lines, and the colors reflecting the complexity, from low, deep blue, to high, bright red. Software World 1999, 119, 120 represented the whole software as a world, a package being a country, a file a city, a class a district, and a method a building. The size of a building represented the numbers of lines of the method, the number of doors the number of parameters, and the number of windows the number of declared variables. The color of a building indicated whether the method was private or public. Immersive, Immersive Software Visualization, 2001, 122, 123 represented a class with a platform whose size encoded the total number of methods and attributes. Attributes were represented as red spheres near the platform, their size encoding their type. Members' functions were represented by columns placed on them. Platforms with colors encoding their type, i.e. constructor, accessor, and modifier, and height the number of lines of code. Skyscraper 124 considered software evolution. The user could look at the evolution of the city by moving between multiple versions of the software. This allowed representation of attributes such as code churns, number of modified, added, and deleted lines over the life of a file, and biggest lines of code, highest number of line for a file based on all its versions. These were represented within the building metaphor with building height linked to code churn, the base area encoding the current lines of code, while a green square at the bottom represented the surface occupied by the building in its biggest state using a garden metaphor. Such representation quickly allowed maintainers to see which part of the code had gone through many changes, skyscrapers, or to find deprecated functions, large gardens with tiny buildings. ExploreVis proposed a novel attribute representation by showing communications between packages as orange lines whose widths encoded. Call frequencies 125, 126. Few systems used visual mapping to provide additional information about graph data attributes. Genome 3D Explorer 115 allowed the exploration of the yeast gene block duplication. Chromosome database nodes were represented as spheres, their values being encoded by size, shape, transparency, and color. The values of edges were encoded by length, shape, transparency, and color. Russo dos Santos et al. 121 also proposed a metaphor of a solar system to represent network services data. Sound and haptics were not exploited for graphs and trees data representation in the papers of our corpus. A unique paper falls outside Nesbitt's taxonomy by exploring the use of smell for cryptocurrency market analysis, 132. The average transaction rating of an entity was converted into a nominal attribute with 6 distinct values and displayed through 6 different smells, such as citrus or floral. 3.6 Discussion. IA systems cover a wide spectrum of datasets and analysis objectives, from scientific visualization of CFD simulation or brain data to software visualization. This huge variety of works leads to additional complexity when it comes to federating a community and building best practices, though. 7. Few attempts in that direction have been made for multidimensional data representation, 104, 133. Some trends can also be noted in specific domains. Software visualization, often used a city metaphor, multi-dimensional datasets have mainly been visualized with 3D scatter plots, and oceanography and climatology solutions always used isosurfaces and vector fields. Last, despite the multisensory aspect of IA, the focus of research is heavily biased toward visual representation. Only 2 papers in our corpus made use of the haptic channel to encode information, and sound has been scarcely used. Interactions. This section is dedicated to presenting the interaction modalities for the IA systems in our corpus, organized by data analysis tasks. The tasks are taken from the taxonomy of Bremer and Munzner 18. We chose it over the taxonomy of Laha et al. 153, whose goal-oriented approach did not fit our focus on interaction, and that of Keefe and Eisenberg 154, which is more interaction-oriented but lacks critical low-level tasks, such as annotate or record. Table 2 gives an overview of the tasks and main interaction modalities. Tasks have been subspecified into categories to further structure the subsections. For point 1, navigate. The navigate task covers interactions that alter the viewpoint of the user. Most immersive technologies include head tracking, allowing their users to navigate virtual worlds with physical movements. Additional navigation modalities must, however, be implemented when the total volume of the visualization becomes bigger than the available physical space. Only boom solutions, where movement range is determined by the robotic arm, altered the one-to-one movement law between the user head and the camera displacement by having a faster virtual movement outside of the data volume, 14. All other solutions have used additional control that we categorized as follows: walking/flying, scaled world grab, world in miniature, and zooming. Walking, gliding, is a classical movement modality for applications based on first-person view, such as video games. It is therefore popular for IA systems. For example, GeoVisor allowed movement over agent 2D map 52 using the input from a VR controller's joystick. Flying is a 3D movement that requires an additional direction. In general, the orientation of the wand or VR controller serves this purpose. 39, 75, 95. WorldGrab proposed a different way to navigate through an immersive environment by moving the position of the visualization instead of that of the user. Swipe gestures have been used to pan the visualization in 2D, either by tracking a data glove over a workbench display, 34, or by detecting classical swipe gestures on a touch table associated to an AR display, 64. 110. ExploreViz used a metaphor of grab and drag, 125, 126, a fist gesture, captured by a Kinect V2, followed by a drag movement with the right hand translating the visualization. For 2D rotation, Shin et al. 62 used a joystick input from the wand in a cave, while La Viola Jr. et al. 34 proposed a two-finger pivot gesture with 1077 to 2626, see 2019 IEEE. Personal use is permitted, but republication/redistribution requires IEEE permission. seep//www.ieee.publications_standards/publications/rights/indexed him for more information. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IEEE Transactions on Visualization and Computer Graphics JOURNAL-OFTVCG, VULD XX, NO.X, month 2019-8, Table 2, Overview WOF Interaction Tasks in iLiterature Task Category Interaction References Walking, Gliding, / Flying Direct Controller Input, 39, 52, 75, 95, Direct Controller Input, 62, 70, 134, Markers Displacement, 107, 124, World Grab Hand Gesture, 34, 87, 125, 126, Grab Move Release, 41, 66, 67, 135, World in Miniature Swipe Gesture, 64, Direct Controller Input, 124, 136, Virtual Menu, 35, Magnifying Glass Metaphor, 39, 39, 81, 81, Navigate Zooming Hand Gesture, 34, 125, 126. Raycasting, 35, 55, 75, 79, 95, 106, 112, 122, 123, 137, Single Object Swipe Gesture, 138. Brushing, 98, 127, 136, Select Multi-Object Box Selection, 36, 39, 139, 140, 141, Pop-up window, 35, 55, 75, 95, 112, 137, 138, 360 photo, 137 reactive interactive lens, 142 gaze, 143 predictive proximity, 78 text information, 122, 123, 144 details and demand TUD screen multimedia information, 106 grab move release, 145 heat model, 30 data point attraction model, 78 grab move release, 14, 21, 34, 70, 146 view components touch press, 110 arrange views grab move release, 69, 95, 129, 138, 147 opacity 50, 81 glow, 122, 123 highlight 3D GLYPH, 29, 102 data position axis, 41, 110 mapping data visual, 39, 94 change representation dash 52, 107, 129, 148, box selection, 36, 39, 139, 140, voice command, 34, direct selection slices election, 128, visual menu, 65, 75, 82, 94, voice command, 115, filter abstract layer in body control, 64, 134, 148, aggregate edge bundling dash 148, free annotation dash 149, annotate predefined annotation dash 150. Load nuditacid dash 65, import load nuditailment dash 42. Derive undo selection dash 39, record visualization state dash 29, 34, 151, 152, record video dash 34, a data glove over a workbench. Multiple solutions have been implemented for 3D rotation, grabbing off the visualization box without a toll of 87, perform mingafist and dragesture, 125, 126, physically rotating a fiducial marker, 107, 124, or rotating gas specific controller, based on the shape T visualization. Its orientation being directly connected with the visualization orientation, 70, 134. World in miniaturelos navigation while keeping the context in mind by providing a scaled-down version of the visualization for Theasur Tacos where he will be teleported. Archive, 66, 67, Wizard, 41. Interactive Slice WM, 64, and Bima, 135, System Suicided. They all had a Tavalum representations by Foresters to easily losathican text off their position. Zooming. Multiple input types have been used for zooming. Keyboard, 124, controller buttons, 136, 3D menu selection, 35, or hand gestures, 34, 125, 126, Asanexum. PLE, for the latter, explore visaseta pushing gond pulling box. Metaphor. Zoama kurswin both closed hands approach theater so thurzer, whileo peening both hands and pushing themawe from the torso trigger sunzome. Other systems feature a virtual tool such as Manify Glass Grabbed with Data Glove, 39, 81. Aura Stylus, 36, 140. The movement of the input device changing the visualization scale. 4.2 select task covers data point, S, selection. In general, this is to activate details on demand, C4.3, highlight, C4.5, or filtering, C4.6. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information, DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Single object selection. IA systems in our corpus all relied on raycasting, with differences in raycast source and orientation. ExploreVis 122, 123, Dragon 35, Cavesum 112, and Dis et al. System 79 all used a wand. The origin was the position of the wand, and the ray direction was mapped on its orientation. Obelisk XR 137, Idea 75, and the River Disaster Management System of Reddy et al. 95, applied the same principle replacing the wand behavior controller. VR Miner 106 detected a pointing gesture of the data glove to activate the raycast, using index orientation as direction. The Maritime Smuggler Detection System of Franz et al. 55 used the head tracking of the Microsoft HoloLens to produce the raycast. The head position defined the origin and the user gaze provided the direction. Keefe et al. 138 went a bit further. The raycast was first used to select a general zone of the visualization, then a swipe gesture on an iPod Touch allowed to move the selection in the direction of the swipe for higher precision. The use of one finger or two fingers for the swipe determined the distance of the jump to the next object. Multi-object selection. Two approaches have been explored for multi-selection. The first technique, brushing, has been implemented in Lechner et al. 127 and Brunhart et al. 136 systems with a similar principle. Users grabbed a virtual tool, represented by a lamp, that projected a cone with a limited height. Any data point entering in contact with the cone was selected. Fiberclay 98, a system to analyze planes' trajectories, used a simple raycast for brushing. Any trajectory that came into contact with the raycast, activated by pressing the trigger of a VR controller, was added to the selection. Performing the same action with the second controller removed trajectories from the selection. The second technique relied on box selection. In the Cosmic Explorer 139, for visualization of galaxy formation simulation, the user could select a slice of the visualization volume through a series of hand gestures tracked by a data glove. Slice selection was possible for all three main coordinates, resulting in the equivalent of a box selection. In the Virtual Data Visualizer, users grabbed a box virtual tool with a wand that activated the zone selection mode. 39. A diagonal of the cube was defined by pressing a button twice, each press defining a point of the diagonal at the position of the wand. The cube was oriented parallel to the world coordinates axis. Henschel et al. System 141 used the same method. DeHaan et al. Proposed the Plexipad 36 140 to offer free orientation of the selection box. Plexipad was a square of plexiglass with a 6-degree of freedom tracker. The first face of the box was defined by the face of the Plexipad, while the last point needed to define the full geometry was positioned with the help of a tracked stylus. 4.3 Details on Demand. This task covers interactions aimed at displaying detailed information about the data. Some approaches take place inside the virtual environment. Others make use of an external 2D screen. Reactive approaches. The most common way to get details on demand is a simple single-object selection, followed by the appearance of a pop-up window filled with text information. For instance, the Dragon System 35 displayed all. 9. The details of a selected Army unit, a similar approach being used for boat or drone entities in the Maritime Smugglers Detection System 55, Neuron Information in the CaveSim 112, Demographic Data in Keefe et al. System 138, and Logs and Idea 75. The River Disaster System of Reddy et al. 95 displayed a 2D curve of the weather sensor value over time. The Obelisk XR 137 also used a pop-up window to present detailed information about the selected stone, one characteristic being that it could then transport the user into a 360 photo of the location where the stone was extracted, upon selection of the location value in the pop-up window. Last, Moda et al. 142 proposed a spherical virtual lens to enrich the representation of the delimited zone for multi-geometry 3D visualization. The lens position was directly controlled by the movement of a VR controller. Predictive approaches. Another way to get supplementary information related to objects is to try and automatically determine the interest of the user. For instance, Infoticals displayed the labels of the particles close to the user, 78. In 143, multiple 2D maps of oil spill simulation were visualized through a Microsoft HoloLens. They were positioned on top of each other, the one looked at by the user being scaled up while the others moved aside. Additional 2D screen. The use of a second screen has been explored in IA systems. Immersive displayed the C++ source code of the selected class or method directly on a 2D screen next to the cave. 122, 123. Azag et al. 106 used a second screen located next to their main 3D screen to display multimedia data, e.g. images and videos. Baumgartner et al. 144 allowed users to grab, with a data glove, a data point representing a document from their 3D screen and move it on top of a tablet, resulting in the full document text appearing on the tablet. For point for arrange. The arrange task refers to interactions that spatially organize visualization elements. The following describes proposals to organize data points, view components, and multi-views. Arranging data points in IA systems is rare, due to the fact that their positions are used to encode information. Infoticals, 78, used an indirect solution to manipulate data points particles. The user could create an attractor object which was associated with a particular value for an attribute. Any data sharing the same value as the attractor for this attribute was then attracted by it. Osawa et al. 30 proposed a node/edge 3D representation of network data. Nodes were initially placed with a force-directed placement algorithm, but they could be heated to change their positions. Each node, indeed, possessed a virtual temperature. The higher its temperature, the more the other nodes would be repelled from it. Edges could also transport temperature, so nodes linked to a heated node became heated, which made the network of the selected node more apparent. Users could adjust a node temperature with a data glove by touching it with their fingers, opening their thumbs, and doing a rotation of their wrists. They could also create a heat cone to affect multiple nodes at the same time by pointing the index finger without touching a node, the opening of the thumb defining the cone angle. Nodes could also be. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. Locked in place by pinching them with the index finger and thumb band hand-to-engrossed rotation, mimicking a key into keyhole movement. Last, Ejing et al. 145 allowed users to arrange nodes and edges through direct hand gestures, making a fist to grab the object, then moving the hand before opening the fist to lock it in a new position. Arranging view components can be found in CFD. Data gloves-equipped users could move particle injectors to new positions, either through pinch gestures followed by a movement, 14, 21, or by using voice commands to grab the element closest to the hand, followed by a movement, and then a drop. Voice command, 34. RSVP system, 146, and the seismic cube visualization, 70, showed 3 2D slices perpendicular to each main axis. RSVP proposed a slider control over a 2D UI, while FR Olich's system used a specific controller called the cubic mouse, which allowed lateral positioning of those slices with sliding rods which went through the whole controller. Each rod was on a different face of the cube to make the relation to its associated slice intuitive. In their parallel coordinate system for presenting 2D scatter plots on top of a touch table, Butcher et al. 110 provided the possibility to invert the axis of one representation with a touch press on a menu button. Arranging views. Most of the systems in our corpus use the same paradigm, namely grab, move, release. Each proposal uses a specific input to link the movements of the controller to the movements of the view until another input discards the link. Salfeld et al., 69, added virtual windows around their multiple views, taking inspiration from computer windows. Grab was done by a button press when a raycast projected by a stylus was in contact with the title of the window. Release was done by the same button press. Reddy et al. 95, River Disaster Management System allowed to arrange pop-up windows by grabbing them with a trigger input while in contact with the window, while release was done via the same trigger. Keefe et al. 138, Demographic Analysis Tool allowed the user to arrange details on demand windows by selecting them, then moving them around through swipe gestures on an iPod Touch. IMAX's 129, let users build their own visualization. By grabbing and arranging axes, see 4.5, thus creating multiple views. A view could be grabbed by pressing a trigger on the VR controller while in contact with the view volume, and release was done by pressing the trigger again. A similar solution was used to arrange views for dice model visualization, 147. For 0.5 change. The change task refers to interactions that alter visual encoding. This includes highlight of specific data points, changes in attribute mapping for one representation, and changes of representations. Highlighting. One way to highlight data points is to control their opacity. Wesk et al. 81 implemented in the CFD system the possibility to change the opacity of a particle injector, which in turn changed the opacity of all its outgoing particles. To do so, the user grabbed a virtual tool and placed it in contact with the particle injector, followed by a wrist rotation to determine the resulting opacity. Moran et al. 50 allowed a user of their tweet analysis system to change the 10 opacity of the buildings with a virtual menu activated by a leap motion hand gesture. The 3D scatter plot proposed by Szymanczyk et al. 102 featured a preset of 3D shapes that could be grabbed with a pinch gesture of the data glove and put in contact with data points to change their appearance. Arms et al. 29 used a virtual brush tool metaphor. The user could create a virtual brush with specific color, size, and shape selected from a raycasting pointing gesture of the data glove, and then touch data points of the 3D scatter plot to change their color, size, and shape accordingly. The software visualization system ExploreVis 122-123 allowed users to quickly display relationships between entities. Overloaded methods were highlighted with a glow effect when the user selected a method by placing the wand on top of it. Changing attribute mapping for one representation is done by using menus in all the systems in our corpus. iFlight 94 used a 3D menu with raycasting selection to switch between two color mappings related to bees' roles or behaviors, or change the environmental variable isosurface representation. Butcher et al. 110 system allowed changes to the dimensions displayed on the 2D scatter plot axis of their 3D parallel coordinate representation via a touch table menu. Selected 2D scatter plot appeared on the table, and the user could touch an axis to display a list of the dataset attributes, then select one. The wizard system, 41, used one-handed interaction to select the variables displayed on each axis of a 3D scatterplot. A menu was displayed on top of the user hand. Each phalanx had a button on top of it, and the thumb was used to press on the selected buttons. The user first selected the axis, then the attribute to map to it. The Virtual Data Visualizer, 39, could group data into classes that the user could map to a specific 3D glyph. Using a workbench metaphor, class selection was done via a 3D menu with raycasting selection from the wand, shape selection by grabbing a 3D model from a drawer, color by pointing on a color map on top of the workbench, and size with a slider on top of the workbench. Changing representations. GeoVisor 52 used VR controller button press to switch through available representations such as 3D scatter plot, 3D parallel coordinates, or node link diagrams. Herder et al. 148 represented a 3D cubic volume of plane trajectories in AR with HoloLens. If the user physically stepped inside the volume, the representation changed into 2D projections on each face of the 3D volume. As seen earlier, IMAX's 129 allowed users to build their own multidimensional data representation. Grabbing, moving, and releasing the relative positions of axes with a veer controller changed the representation, for instance, from 2D scatter plot to parallel axes. Megan's et al. 107 allowed the users of their mobile AR system for multidimensional data analysis to generate histograms or pie charts to be displayed in conjunction with a 3D scatter plot. To do so, the user could interact with a virtual menu by occluding buttons with his hand, selecting the type of the additional graph, as well as the attribute to be visualized. For 0.6 filter. Filters determine exclusion or inclusion criteria for visualization elements. Filtering interactions can be done directly on the visualization or by manipulating an abstract layer. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033,